All right, let's go. Number 10, the runaway. In 2019, astronomer Sergei Kopasov of Carnegie Mellon University was analyzing spectroscopic data from the Southern Stellar Stream Spectroscopic Survey, known as S5, when his team identified a star moving at a velocity that forced a recalculation. The star, designated S5-HVS1, had been observed using the 3.9-meter Anglo-Australian telescope's 2DF fiber positioner at Siding Spring Observatory, with its motion refined by astrometric data from the European Space Agency's Gaia satellite. The results, published in monthly notices of the Royal Astronomical Society, confirmed a speed of 1,755 kilometers per second. That's approximately 6 million kilometers per hour, 0.6% the speed of light. For a star, that number is almost nonsensical. But what the light carries when you split it into a spectrum is a trajectory. And this one points straight back to a monster. Tracing S5-HV, S1's path backward through 4.8 million years of galactic motion leads to a single point of origin, the immediate vicinity of Sagittarius A star, the supermassive black hole at the center of the Milky Way, an object 4 million times the mass of the Sun. The ejection mechanism had been theorized in 1988 by astronomer Jack Hills. A binary star system wanders too close to a supermassive black hole, tidal forces rip the pair apart, one star is captured, and the other is flung outward at extraordinary speed. S5-HVS1 is the first confirmed example of this process ever observed. The star is an A-type main sequence object, roughly 2.35 solar masses, unremarkable in every respect except its velocity. Though it is traveling fast enough to permanently escape the gravitational pull of the entire Milky Way galaxy, it will never orbit back, it will never return, it will cross into intergalactic space and continue alone indefinitely. A black hole 4 million times the mass of the Sun ripped a binary apart and threw the survivor into the void. It's still running. Number 9, the impossible radiation. In October 2023, the HESS collaboration, operating the high-energy stereoscopic system, an array of 5 Cherenkov telescopes in the Comus Highland of Namibia, published a result in Nature Astronomy that quietly broke a fundamental assumption in pulsar physics. The lead researchers, including Arake Janati Atai of the APC laboratory in Paris, Emma de Onya Wilhelmi of DESY in Germany, and Bronek Rudok of the Copernicus Astronomical Center in Poland, had been observing the Vela Pulsar, a rapidly spinning neutron star roughly 1,000 light-years away, the collapsed remnant of a supernova that occurred about 11,000 years ago. What they detected were pulsed gamma rays reaching energies of 20 tera-electron volts. What makes this deeply unsettling isn't the energy, it's that no known physics can produce it. To put 20 tera-electron volts in context, it is 200 times more energetic than any previous detection from this pulsar, and 20 times higher than the Crab pulsar, the only other pulsar previously observed at tera-electron volt energies. Every standard model of pulsar emission, curvature radiation, synchrotron radiation within the magnetosphere predicts a hard cutoff at a few giga-electron volts. None of the particles responsible for this radiation would need to be accelerated to Lorentz factors exceeding 40 million, a regime no existing theoretical framework can account for. The emission represents an entirely new spectral component, distinct from the well-characterized lower energy radiation, maintaining phase coherence with the pulsar's rotation, yet emerging from a physical mechanism that has no name. Proposals exist: inverse Compton scattering beyond the light cylinder, acceleration in the pulsar wind zone, but each remains speculative, and none has been validated against the data. The HESS team confirmed the detection over 80 hours of observation. The signal is real, repeatable, and unexplained. Every model says this radiation can't exist. The pulsar doesn't care. Number 8, the chirp. In December 2024, a superluminous supernova was identified in survey data and designated SN 2024 AFAV. Over the following months, a team led by Joseph Farah of UC Santa Barbara and the Las Cumbres Observatory monitored the event for more than 200 days using the observatory's global network of 27 telescopes, alongside contributions from researchers including Andy Howell at Las Cumbres, Logan Proust of the Flatiron Institute, and Alex Filipenko of UC Berkeley. Their findings were published in Nature in March 2026. The supernova had initially been classified as a Type 1 superluminous event, extraordinarily bright but within known categories. Then the light curve did something no supernova has ever done. As SN 2024 AFAV faded, its brightness didn't decline smoothly. Instead, it oscillated. 4 distinct brightness bumps appeared in the decay phase, so each separated by a shorter interval than the last. The pattern was a chirp, a signal accelerating in frequency over time. Previous superluminous supernovae had shown at most one or two bumps attributable to interaction with surrounding material. 4 bumps with a compressing cadence was unprecedented, and the team explored every conventional explanation before arriving at the only mechanism that fit: lens-Thirring precession. This is a prediction of general relativity. A massive spinning object drags the fabric of space-time around itself, causing nearby structures to wobble. In this case, a newborn magnetar, a neutron star with a spin period of roughly 4.2 milliseconds and a magnetic field of approximately 3 × 10 to the 14th power Gauss, had formed inside the supernova debris. Asymmetric fallback material created a misaligned accretion disk, and the magnetar's frame dragging caused the disk to precess, periodically modulating the energy output. This marked the first time general relativity was required to describe the mechanics of a supernova, and the first directly witnessed birth of a magnetar. For the first time, we watched a dead star's corpse twist space-time around itself in real time. Number 7. The star that broke the limit. Between 1837 and 1856, astronomers across the southern hemisphere watched a star in the constellation Carinae undergo an eruption that defied every known principle of stellar physics. Eta Carinae, a massive binary system roughly 7,500 light-years from Earth, brightened until, in March 1843, it became the second brightest star in the entire night sky, outshone only by Sirius, which sits less than 9 light-years away. The energetics of the event have been studied extensively by Nathan Smith of the University of Arizona, while in 2012, astronomer Armin Rest at the Space Telescope Science Institute discovered light echoes from the original eruption. Ancient light that had bounced off interstellar dust and arrived at Earth with a 170-year delay. Published in Nature. Separately, Setonir Shaviv of the Hebrew University of Jerusalem proposed a porous atmosphere model to explain how the star could exceed its theoretical limits. The Eddington limit is the line where radiation should tear a star apart. Eta Carinae crossed it by a factor of 10 and survived. During the Great Eruption, the star ejected between 10 and 20 solar masses of material in roughly a decade, forming the Homunculus Nebula, a structure visible in modern telescope images. The mass loss rate exceeded several solar masses per year, millions of times greater than any stellar wind model can produce. The kinetic energy of the ejected material alone, approximately 10 to the power of 50 ergs, rivals that of a low-energy supernova, yet the star did not explode. It did not collapse. It remained intact. Yet Rest's light echoes revealed something else unexpected. The eruption temperatures were only about 5,000 Kelvin, far cooler than any explosion model predicts. A deep-seated blast should have produced temperatures an order of magnitude higher. After 180 years of study, every proposed mechanism fails to account for all the data simultaneously. The Super Eddington wind model cannot explain the total energy. The deep explosion model cannot explain the low temperatures. The binary interaction model cannot explain the duration. It exceeded the theoretical limit for its own existence by an order of magnitude. And it's still there, waiting to do it again. Number 6. The star with no iron. On February 9, 2014, a team led by astronomer Stefan Keller and spectroscopist Mike Bessel at the Australian National University published a paper in Nature that described a star unlike anything in the existing catalogs. The object, bearing the designation SMSSJ031336-6708393.3, had been photometrically identified on October 2, 2012 by the SkyMapper telescope at Seeding Spring Observatory and confirmed through high-resolution spectroscopy with the 6.5-meter Magellan Telescope's Mike Eschel spectrograph at Las Campanas Observatory in Chile. Anna Frebel of MIT contributed to the analysis. What Keller's team found was a red giant roughly 6,000 light-years away in the constellation Hydrus, with no detectable iron whatsoever. The absence isn't a gap, it's a message from the first generation of stars, and what it says rewrites how they died. The upper limit on iron abundance was measured at less than 1/10,000,000th of the Sun's iron content, 30 times lower than the previous record holder. In any stellar catalog, this star sits alone at the bottom, but the spectrum wasn't empty. Carbon was present at levels over 1,000 times greater than the iron upper limit, alongside traces of magnesium and calcium. This specific chemical pattern, carbon-rich, iron-absent, tells a story about a single event, the death of one of the very first stars in the universe. The composition implies that the primordial supernova which seeded this star's birth cloud was a low-energy event, powerful enough to eject its carbon-rich outer layers but too weak to expel its iron core, which instead collapsed into a black hole. This was unexpected. For decades, theorists had predicted that the first stars, a massive population 3 objects, died in energetic pair instability supernova that would have rapidly distributed iron across the early universe. This star's chemistry says otherwise. The first generation may have died quietly, swallowing their heaviest elements. The first star that ever died near this one didn't explode. It collapsed and took its iron with it. Number 5. Older than the universe. In 2013, astronomer Howard Bond of Penn State University and the Space Telescope Science Institute published a study in the Astrophysical Journal Letters that presented a problem no one has fully resolved. Bond's team had spent nearly a decade observing a single star, HD 140283, like a metal-poor subgiant in the constellation Libra, located roughly 200 light-years from Earth, using the Hubble Space Telescope's fine guidance sensors across 11 separate observation sets between 2003 and 2011. The goal was simple: determine the star's parallax with unprecedented precision, then use that distance to calculate its age. The result was 14.46 billion years, plus or minus 800 million. The implication nobody wants to say out loud is arithmetic. The age of the universe, as determined by the Planck satellite's measurements of the cosmic microwave background, is 13.787 billion years, plus or minus 20 million. The central age estimate for HD 140283, nicknamed the Methuselah Star, places it approximately 660 million years older than the universe itself. The error bars technically allow the two numbers to overlap, but every refined measurement has stubbornly refused to drop the central value below the cosmic age. A 2025 Astro-C ismology study produced an independent age estimate of roughly 14.2 billion years, still exceeding the universe's age at face value. The star's metallicity, iron abundance roughly 1/250th of the sun's, confirms it as an ancient population 2 object, one of the first generations of stars formed after the Big Bang. Gaia's third data release placed the star slightly farther away than Hubble's measurement, which in principle should reduce the derived age by increasing the inferred luminosity. It helped, but not enough. The tension persists. 2 possibilities remain, and neither is comfortable. Either the stellar age models contain a systematic error that consistently overestimates the ages of metal-poor subgiants, or the universe's age, one of the most precisely measured quantities in all of science, is wrong. Either this star is lying about its age, or the universe is lying about its own. Number 4. The star that vanished. In 2009, astronomers monitoring NGC 6946, a spiral galaxy roughly 22 million light-years away, informally known as the Fireworks Galaxy for its unusually high supernova rate, observed a 25 solar mass red supergiant brighten to approximately 1 million times the luminosity of the Sun. The brightening was consistent with the early stages of a supernova. Then the star disappeared. No supernova was recorded, no expanding shockwave, no remnant nebula. The star simply ceased to be visible in optical wavelengths. The object was designated N6946-BH1, and for over a decade it stood as the leading candidate for a failed supernova, a theorized event in which a massive star's core collapses directly into a black hole without producing an explosion. Here's where it becomes something worse than an explosion. It's an absence. In 2023, astronomer Emma Bieser of the University of Arizona led a team that turned the James Webb Space Telescope on the location, using both NIRCam and the mid-infrared instrument, and published the results in the Astrophysical Journal. What JWST revealed was that the object previously identified as a single star was actually a blend of at least 3 separate sources, previously unresolvable by Hubble or ground-based telescopes. The combined infrared luminosity of these sources accounts for roughly 13 to 25% of the original progenitor's brightness. The mid-infrared spectrum shows polycyclic aromatic hydrocarbon features consistent with dust illuminated by ultraviolet radiation. 2 scenarios remain viable. The 2009 brightening was a stellar merger, two stars colliding and being misidentified as a pre-supernova event. Or it was a genuine failed supernova, and the residual sources are fallback material around a newly formed black hole. A JWST Cycle 4 follow-up program has been approved, 16 hours of dedicated MIRI spectroscopy and multi-epoch monitoring designed to finally resolve the question. If confirmed as a failed supernova, it would be the first direct observation in human history of a star becoming a black hole. A star 1 million times brighter than the sun was there, then it wasn't, and nothing came out. Number 3. The zombie. In August 2017, astrophysicist Stefan Venes of the Czech Academy of Sciences published a paper in the journal Science describing a white dwarf that should not exist. So the object designated LP40-365 had been observed using multiple instruments, including those at Kitt Peak, the William Herschel Telescope, and Gemini North. What Venens and his colleagues found was a stellar remnant traveling at 852 kilometers per second over 1.2 million miles per hour, fast enough to permanently escape the Milky Way. Subsequent analysis by J.J. Hermes at Boston University using test data and Roberto Ratti at the University of Erlangen-Nuremberg using Gaia kinematics confirmed and expanded the findings. What shouldn't exist isn't the explosion, it's what walked away from it. LP40-365 is the remnant of a white dwarf that was caught in a thermonuclear supernova, a Type 1a, or more precisely, a Type 1ax event, and survived. Standard supernova physics says the white dwarf should be completely destroyed in the detonation. LP40-365 didn't get the message. Its atmosphere is composed almost entirely of oxygen and neon, with traces of sodium, magnesium, and other intermediate mass elements. Hydrogen and helium, the two most abundant elements in the universe, are completely absent. The manganese-to-iron ratio is 7 times solar, a chemical signature that can only be produced inside a thermonuclear explosion. The star is roughly 15 times larger than a typical white dwarf, bloated as though inflated by the energy of the detonation that should have annihilated it, and its mass is only about 0.14 solar masses, far below what any deflagration model predicts for a survivor. There is a related object that makes this stranger, the central star of the nebula PA30, now connected to SN 1181, a supernova recorded by Chinese and Japanese astronomers in the year 1181 AD. Was confirmed in 2021 by Albert Zielstra and colleagues as another zombie white dwarf. That star survived its own supernova 844 years ago. It is still burning, and its surface is among the hottest in the Milky Way. It survived a thermonuclear explosion that should have erased it from existence. Now it's flying out of the galaxy carrying the scars. Number 2, the star that died twice. In September 2014, the Intermediate Palomar Transient Factory, an automated survey operating the 48-inch Samuel Oshine telescope at Palomar Observatory in California, flagged a new transient in the constellation Ursa Major, roughly 500 million light-years from Earth. It was designated IPTF-14HLS and initially classified as an ordinary Type 2 P supernova, the most common kind, characterized by a plateau in brightness lasting about 100 days before fading. The supernova was expected to follow the script. It did not. Over the following months, a team led by Yair Arkavi of Tel Aviv University and the Las Cumbres Observatory, supported by observations from the Keck 1 and Keck 2 telescopes, the Hubble Space Telescope, and the Neil Gehrels Swift Observatory, watched IPTF-1, 4, HLS brighten and dim at least 5 times over a span exceeding 600 days. The temperature held steady at roughly 5,000 to 6,000 Kelvin. The total radiated energy reached 3.59 times 10 to the 50th erg. By every metric, the supernova was behaving as though it had just occurred again and again while refusing to fade. And then they checked the archives, and the nightmare doubled. When Arkavi's team examined Palomar Observatory sky survey plates from 1954, they found a previous explosion recorded at the exact same celestial coordinates. The star had exploded 60 years earlier, survived, retained tens of solar masses of hydrogen, which should have been stripped in the first detonation, and then exploded again. The leading theoretical explanation is a pulsational pair instability supernova, a process predicted only in stars between 95 and 130 solar masses, where the core becomes so hot that photons convert into electron-positron pairs, triggering violent eruptions without full stellar destruction. But the energy output exceeds pulsational pair instability predictions. the hydrogen retention is not predicted. And such events were thought to be confined to the earliest, lowest metallicity stars in the universe, not to a star in a galaxy 500 million light-years away in the modern epoch. Archivi himself summarized the situation. There is no existing model or theory that explains all of the observations. A star exploded in 1954. It came back. It exploded again. And no one can explain why it's allowed to do that. Number 1. The impossible elements. On April 26, 1961, the Polish-Australian astronomer Antoni Przybylski published a brief paper in the journal Nature describing the spectrum of a star he had observed at Mount Stromlo Observatory near Canberra using the 74-inch telescope's Zeiss spectrograph. The star, designated HD 101065, roughly 356 light-years away in the constellation Centaurus, exhibited a spectrum that Przybylski could not reconcile with any known stellar classification. Common elements like iron and nickel, which dominate the spectra of most stars, were mysteriously weak. Rare earth elements, holmium, dysprosium, samarium, were overabundant by factors of 1,000 or more. The anomaly deepened in 2004 when a team led by Vera Gopka and Alexander Yushchenko identified spectral lines corresponding to short-lived actinide elements: actinium, protactinium, neptunium, plutonium, americium, aucurium, berkelium, californium, and einsteinium. Every other entry on this list broke a rule. This one breaks the periodic table. These are not elements that belong in a stellar atmosphere. Einsteinium was first synthesized on Earth in 1952 inside the debris of the first hydrogen bomb test. Promethium, tentatively identified by Charles Cowley and colleagues in the same period, has a half-life of just 17.7 years. In the time it takes a human to go from infancy to adulthood, half of any promethium present will have decayed into something else. For these elements to appear in a star's spectrum, they must be continuously produced or replenished by an ongoing process. No known stellar mechanism achieves this. In 2017, physicists Vladimir Dzuba, Victor Flambaum, and John Webb proposed a hypothesis. The observed actinides are decay products of undiscovered superheavy elements occupying the theoretical island of stability, a predicted region of the periodic table where elements with specific neutron numbers might resist rapid decay. These elements have never been created in any laboratory. Their existence is inferred from nuclear physics models but remains unconfirmed. The star's rotation period, measured by Svetlana Hubrig and colleagues using ESO's Harpsball spectrograph and published in monthly notices of the Royal Astronomical Society in 2018, is approximately 188 years, one of the slowest stellar rotations ever recorded, deepening the mystery of how its surface chemistry could be maintained. What the light carries from this star isn't just a spectrum, but it's a chemical fingerprint that doesn't belong to any known process in the universe, not stellar nucleosynthesis, not supernova enrichment, not neutron capture in any documented environment. There is a star 356 light-years away with elements on its surface that humanity has only ever produced inside nuclear reactors and hydrogen bombs. No one knows how they got there. No one knows what's making more. If you want to see more videos like this, click the video on screen now and make sure to subscribe.